Hi everybody, welcome to this lecture covering Chapter 2, the first portion of Chapter 2 through Section 2.3 in Essential Logic for Computer Science by Page and Gamboa, which is the book we're referring to as P&G, and that's the way that book is identified in the Canvas course space. This first lecture is actually pretty important when it comes to computer science to have a firm understanding about the ways in which variables, Boolean variables, can be combined to produce certain effects. So typically when one is building an application that's meant to exhibit forms of artificial intelligence. A lot of the algorithms that get built, say in like robotics, for example, rely very heavily upon extensive formulae, which consist of Boolean expressions, and so you have a range of possible outcomes. And in a program, one wants to be able to select one path of execution over potentially thousands of other paths of execution, and that is determined by expressions, equations, and formulas that utilize various flags, which is a Boolean variable, which is going to assume one of two possible values, true or false. And the other ways in which this type of mathematics is used is in the design of hardware. So a lot of times when a chip is being built, algorithms involving very sophisticated Boolean expressions can be used to guide the development of hardware. And that's something that makes this type of math not only relevant in a course that has as its main focus programming. You could also use this type of analysis in hardware design as well. And interestingly enough, the way these sorts of expressions work, you can also apply these equations to other contexts, such as analyzing text, for example. There are sort of like a set of possible sort of outcomes, and with each additional bit of input, you get closer to what the overall data reflects. And these types of equations, Boolean equations, are very useful for software development and programming for multiple paths of execution. And so here are some equations of numeric algebra. These are pretty straightforward. I would expect that most of you already would sort of be able to realize the reasons why these axioms make sense. So say, for example, some identity, which is the first row in this table. We have a variable x, and we're adding 0 to it. And it doesn't matter what x is, x plus 0 is always going to be x. And then, just with our understanding of negative numbers, negative x plus x is always going to be 0 because those two values equally offset each other, and the result is 0. And even though it may seem obvious, these axioms may seem obvious, it also is possible to write proofs to demonstrate that these axioms or these equations actually work the way they describe they do. And you basically pick up an understanding of these equations working in algebra. And algebra is a very powerful form of mathematics that has great relevance to computer science. In particular, automation and being able to simplify a complex program, and that leads to performance improvement, and that is essentially the reason why software. One of the main reasons why software is modified at all is to make it better, more efficient. And these equations in this slide include variables that assume numeric values. And I think if you think of the value that x assumes, the value that y assumes, the value that z assumes as an integer, that's going to make things a lot easier than having to deal with fractional components. And then the question is, why is minus 1 times minus 1 equal to 1? And what appears here is a proof that's reproduced from the textbook that demonstrates using the axioms or the equations we just looked at. So you can see, for example, that we want to prove that negative 1 times negative 1 is equal to 1. So all the way up here at the top, we have negative 1 times negative 1. All the way down here at the bottom, we have 1. And you can see the steps in between rely upon the equations we just looked at. So for example, identity. Being able to add 0 opens up possibilities for the application of other equations or axioms that we've looked at. And the thing to keep in mind about the axioms, which are over here at the right, over here, so you can see we have some identity, some complement, some associative, product identity, distributive law, some complement, null, commutative, and also some identity. And what we've done is we've taken this initial expression, negative 1 times negative 1, we've added 0 to it, which the some identity axiom says we can do. So we're using the axioms as the basis for the transformations that we're making. And overall, what we want to do is we want to somehow convert negative 1 times negative 1 to 1 without having to make any assumptions other than the axioms, which really, in a way, are assumptions. I think actually, really proving these sorts of expressions or formulae requires, I think, sometimes proofs that can go on and on for hundreds of pages. But when we make some assumptions and we have some axioms to utilize, we can still make progress and prove, theorems by writing proofs. And so we end up adding 0 to negative 1 times negative 1, and then we end up applying the positive complement, which, if you'll notice, we're converting this 0 into negative 1 plus 1, which is the rule, or, the rule that's specified by the some complement axiom. And we make additional transformations, and you can see it gets a little bit sophisticated here in the middle, particularly here when we apply the distributive law. And this ends up with quite a simplification. And you can see once we get past this point that the proof becomes a little bit more predictable. And then we also want to be able to prove Boolean axioms as well. So initially we were looking at formulae that involved integer values, which we were representing using variables such as x, y, and z. And the difference here with the Boolean axioms is we're dealing with variables again. However, the variables aren't numeric, they aren't integers. The variables are a Boolean value. And there are two possible Boolean values, true and false. So you can see here we have some additional operators which enable us to relate a variable with a Boolean value. And some of you may already recognize this V-like symbol as logical OR. And you might also recognize the upside down V down here, and that's logical AND. And then we also have implication, which is an arrow. We have NOT, which is this like backwards looking pipe right here. And we're basically defining axioms. And these are givens that we can utilize as the basis for proofs that we write. So we have, OR identity. And this, if you think about, if you already know how logical OR works, it's not too difficult to see the truth in some of these axioms. So, for example, the only time logical OR is false is when both its operands are false. So you can see X logical OR false is always going to be X. And this is known as the OR identity axiom. We also have OR null, in which X could be either true or false, and the outcome would still be true, provided we're performing logical OR with the Boolean value of true. And so you can just kind of go through these and think about these. And if you've got some skills, working with algebra, it isn't too difficult to see how algebra, the rules of algebra, also apply. So in something like OR distributive, you can see if you just look here that we're basically treating the logical OR as sum and the logical AND as a product. And this axiom here, the OR distributive, makes sense even if we're working with sum and product and variables which assume integer values. However, just keep in mind that we are, in this slide, talking about Boolean values, and a Boolean variable like X or Y or Z, as you see here, is going to assume one of two possible values, either true or false. And like double negation, for example, down here, in which we're knotting X and then we're knotting the result, you can see that the result is just going to be X. And this is something that closely, I guess, parallels the application of negative signs. So if we have two negative signs, we know that the outcome is going to be positive. And the same is also true for logical NOT, which again is this sort of like backwards looking pipe symbol. And that's used to represent the flipping of a Boolean variable from either false to true or true to false. And then we can also prove the way logical NOT works. So we want to prove that not true is equal to false. You can see we have true up here at the top, or not true up here at the top, and false down here at the bottom. and we're applying the axioms that we just looked at to prove that not true is equal to false. And you can see we have self-implication. This true is replaced by false, then false. We then apply implication. We convert the implication to a logical OR with also applying a not to the expression on the left-hand side of the implication. And then we have identity, in which we can simplify what we ended up with when we applied implication. And then going from OR, logical OR identity to false isn't too difficult. We can just apply the double negation rule and we end up with false. So you can see we start with the goal of demonstrating that logical not true is equal to false, and by using the axioms we can convert the first expression into the last expression. So the first expression is what we're starting with, and the last expression is what we're trying to prove. And as long as the transformations that we make rely upon the axioms that were given, this is a perfectly legitimate exercise, and it's typically regarded as a proof. And there's some complexities in applying the rules. It does take a little bit of creativity to find, the simplest proof. Certainly, I think in some cases you might end up with a proof that's long, but nevertheless still demonstrates that what we're starting with is the same as what we end up with. There really isn't any problem with proofs being a bit longer, and I think the more one works with axioms and Boolean equations, I think the easier it becomes to manipulate them. And then we also want to demonstrate that not false is equal to true. So you can see here we have part B of our logical not truth table, and we're applying logical not to false, and we want to prove not false is equal to true. And since we did a good deal of work in the first proof, which we looked at in part A, we can use the result from part A as the basis for this proof, which makes things a whole lot easier. So we know false is equal to not true, and we have to use the parenthesis to indicate that we're now dealing with two logical nots. This makes it easier to read these expressions. And then we can apply double negation just to get true. And so in one step, using the theorem from part A, essentially as an axiom, we're able to show that not false is equal to true.